I will talk about this paper, Towards Guaranteed Safe AI, a framework for ensuring robust and reliable AI systems. And this is a position paper where I and the other authors present and outline a particular vision and strategy for how to create safer and more reliable AI systems. Why should we change anything about what we're doing, right? We have OpenAI and DeepMind and so on have various safety measures that they use for their systems, such as ChatGPT, etc. Why think that those are inadequate? The reason for this is that, okay, while if you're making a chatbot that just answers questions, it's maybe not such a high stakes problem to ensure that the system is safe. However, if we look into the future, of the next decade and the next century, we will want to use AI systems to solve much bigger and more important problems, including things like scientific development, R&D, optimizing various economic measures, integrating them in governance, and so on. And in those kinds of situations, you want stronger guarantees that your systems do what they're meant to do. So, for example, if you build a nuclear power plant, then you have to meet very high safety standards, and you have to be able to demonstrate that your design is safe for some particular way of defining that. If we look now instead on how systems like ChatGPT are controlled, the method that is used there essentially boils down to testing the system a lot, and if you can find an input where it does something bad, add it to the training data. And you keep doing that until you can't find any counterexamples anymore. And this is the fundamental structure of how these techniques work, regardless if we're talking of red teaming or RLHF or inverse reinforcement learning or what have you. And this kind of methodology is fundamentally limited in several ways. First, there is the obvious point that, especially as you use an AI system for some very large and expansive domain, the probability that there will be something you haven't thought of just goes up. You're fighting an exponentially growing number of cases. And indeed, even if we look at just ChatGPT, we know that OpenAI evaluated ChatGPT for several months to gather a huge amount of training data and to try to ensure that it would adhere to their safety standards. And yet it took users, I believe, less than 4 hours to find inputs to jailbreak them. And this also points to the problem that AI systems in the future are also more and more likely to be deployed in adversarial settings where other humans or other AI systems try to break their behavior in some way. And this just requires fundamentally different techniques for dealing with it, right? You can design software for a bank and then conclude that under some large number of hours of normal usage, this banking software doesn't do anything bad. But that would not be enough to trust it. You want some kind of cryptographic hardness protocols, in particular because as you put a lot of money and resources on this software working as it should, then there are greater incentives to break it in various ways. And I think there is also another very fundamental reason for why this type of experimental approach to safety is insufficient for AI systems in particular. And the reason for this is that if you're doing some sort of statistical test of safety, then what you ensure is that your system is safe under the assumption that the testing conditions are representative of the conditions where the system is used. And in machine learning talk, what this means is that you ensure that the system is safe on a particular distribution of environments. But the use of an AI system itself creates new types of situations, right? Especially if we imagine general AI systems or AI systems that are more intelligent than humans. I imagine that running such a systems for even a pretty short amount of time is going to create all kinds of crazy things that didn't happen during testing. And the reason why this is bad is, well, it's just a bigger example of the same kind of thing that goes wrong if you, let's say, test self-driving cars together with human drivers and conclude that, oh, the self-driving car seems to be safe. But then if you replace most cars with self-driving cars, there might be new issues that occur in that type of setting. Or you might have a situation where, for example, once humans are used to the self-driving cars, they drive more aggressively around them, etc. If we accept that those kinds of safety methods are fundamentally limited, there will be a greater and greater need to go to stronger safety measures. Then the question is, how can we get that? And this now leads us to the meat of the method that we're proposing in this paper. And this, which we call guaranteed safe AI, relies on having three components. The first of those is a world model, which is a piece of software that explicitly models the environment in which a particular AI system will be used. And I will talk a little bit more in a moment about what that exactly encompasses and how you can devise that. The second thing that's needed is one or more safety specifications, which express in a formal language various safety properties you want an AI system to satisfy. And then finally, a verifier, which can take an arbitrary, or well, maybe not arbitrary, but at least an AI system that you want to verify, and then produce some sort of formal verifiable guarantee that it adheres to the safety specification relative to the world model. And this is essentially the same kind of thing that is done with formal verification normally. So for example, the software in the autopilot of an airplane will often come with certain formal safety guarantees which show that under such and such condition, the plane won't crash, for example. This relies on having some model of the environment that the plane is used in and a specification of what safe behavior means. And then you produce a certificate that the system satisfies that. But with AI systems, we can imagine doing more general kinds of safety specifications for more general types of systems. So a simple example might be that you want to have an AI system that will never harm anyone, let's say. And creating such a specification is difficult because you need to define what it means to harm someone, and you need to define what it means to cause something to happen, which is more difficult than it sounds like if you haven't tried. Then I will go into a bit more detail on how these three components could be created. So the first is the world model. And I find, at least in my experience, this is the component that people most often ask about. So first of all, what we mean by a world model here is a model that models on some level of abstraction, some part of the world, where what exactly you need to model and what is the appropriate level of abstraction will depend on what you want to use your AI system for, effectively, and also what kinds of safety properties you want to prove about the system. And the reason fundamentally why you need a world model is that without a world model, you can only prove properties about the input-output behavior of an AI system. But in practice, you're often rather interested in input-outcome relations. So to give a simple example, right? Let's say that you have a language model and you want to ensure that this language model will never give advice that is harmful. Well, you can try to define that in terms of the text But really what you care about is something like, oh, well, if you implement what is said in that text, then what downstream effect would that cause if you were to implement that? And that in turn requires you to reason about facts in the world, effectively. I mean, similarly, if you want to have, say, an AI system that generates new drugs, and you want to ensure that it will never generate a drug that would kill a human if it takes it, then in order to formalize that, you need a model of the human body, effectively, that is at a high enough fidelity to determine if a given chemical would harm the human or not.
Keith is asking about the world model.
Yes.
When you're saying world model, are you talking about some trained ML
Yes.
model or something more like a domain model?
Yes, that's very good, and that's exactly what I will get onto now. A thing to note, which we depict somewhat in this diagram here, is that a world model can be created in many different ways, depending on your resources and depending on what type of context you're operating in. And depending on what sort of world model you create, you get different kinds of guarantees. So for example, if you have a very simple environment, you could have a world model that is simply hard-coded by humans. I mean, a simple example of that might be, I don't know, if you're playing a board game, maybe that's not such a high-stakes situation, but in a situation like that, you can create the world model by hand. And similarly, also, if you look at the literature on cryptographic protocols, many of those proofs effectively involve a sort of simple world models that are created by hand. For a more expansive task, that's not feasible, right? That does not scale to any large complexity. So there are many strategies you can use at that point. One option, of course, is to just train a black box world model on data as some giant parameterized neural network or something like that. Now, the risk with this is that you get many of the same issues as you have in the normal case, which is to say, how do you trust the world model? How can you ensure that the world model remains accurate in out-of-distribution problems, etc.? But okay, maybe you can circumvent that somehow, and if you do, that would still be considered to be part of this family of approaches. Other things you can do, for example, is use something like large language models to do something that's more similar to creating a world model manually, but do it more at scale. And so what I mean by this is that if you have language models that can code competently, then you can ask language models to write a giant probabilistic program that corresponds to some type of environment. And then, because the resulting model is interpretable, you can audit it and gain more trust that it's accurate, that isn't just reliant on empirical testing. But because most of the work is offloaded to AI systems, the entire thing becomes much more scalable. There are also approaches with Bayesian machine learning, and I know Joshua Bengio and his group is working on some things in this direction, where the idea basically is to use, or the goal rather, is to generate interpretable hypotheses using a Bayesian method. And if it's interpretable, you can still trust it, even though it's ML generated. And if it's Bayesian, then you can have learning theoretic guarantees that don't overly rely on some sort of on-distribution assumption, which means that you can still get provable guarantees, even though they are statistical. Yeah, and depending on how ambitious you are, or indeed how capable AI systems end up being, you can take this further. So on this extremely ambitious end of the scale, you could attempt to verify that your world models are sound abstractions of our best theories of physics. So to say, for example, well, assuming quantum field theory is true, this particular model is completely accurate within this range of operation. And that would effectively ensure that an AI system can't that would give an extremely high guarantee of assurance. Now, of course, that's harder, so maybe you would want to reserve that type of that level of standard to smaller scale things like verifying that certain sensors or communication channels or hardware properties of your hardware can't be compromised. Yeah, and then I should also mention quickly a common a possible misconception, which is that so the world model does not need to model everything about the world. It just needs to model what is relevant to the safety specification and the context of use for the AI system. And that could be substantially easier than trying to create some kind of model of everything, so to speak.
I have a clarifying question. So do you
Yes.
understand correctly that you propose that there could be different ways of creating these world models, and all of
Yes.
these approaches sort of legitimate?
Absolutely. Well, I mean, what is legitimate is a sort of loaded term. What I am saying is that you can create these models in many different ways. You could use machine learning, you can use automated program synthesis, which, I mean, maybe that counts as machine learning, maybe not, but you could create them by hand. Yeah, so there are absolutely different strategies for creating these world models. You can think of this as these different strategies as sort of being on a spectrum, going from models with weaker guarantees to models with stronger guarantees. And then, depending on what is needed and what is feasible in a particular context, you could gamble on different strategies.
So you're not proposing like one way of modeling the world, right? Like you're just showing the spectrum.
Yes. Yeah. So this is not reliant on a specific method for doing this.
Okay, thanks.
The next point, of course, is the safety specification. And the safety specification or specifications are meant to encode desirable safety properties. And as anyone who has attempted to write a reward function for some complicated environment will know, it's very often quite difficult to encode exactly what you want an AI system to do in a particular situation. And that problem very much carries over to the problem of creating safety specifications. But here again, we can note that a safety specification doesn't necessarily have to encode everything you care about in order to be useful. So, for example, if you have a general AI system on some server, you might have a safety specification that says that the AI system should never copy itself onto any external computers. And that obviously does not encode everything you care about for correct operation of this AI system. But if you could prove that this would not happen, this would give you stronger trust in the system. And this is also the kind of thing that would be easier to formalize directly. As with everything, you can use machine learning also to create these safety specifications, and where, for example, you learn it from data. And then depending on your learning method, you can have different guarantees about the extent to which a learned representation captures your underlying intentions. Another thing to remember also is that it can often be easier to specify safety properties if you have a world model than if you're just trying to specify it sort of in general for an input-output relation. So for example, if you have an AI system that, say, drives a car, and you want it to never crash under normal operation for some way of defining that, then defining what counts as a crash within some simulator could be very easy. even though specifying a, say, sequence of inputs to the AI system that counts as a crash, including the visual, audio, and radar readings of that might be much, much more difficult. So this is also something that is worth keeping in mind. Yeah, and there is absolutely more to say about this, but in the interest of time, I won't go more into those details unless you want to talk more about that in the Q&A. And then finally, we need a verifier. So the verifier is the thing which produces some type of auditable guarantee that your AI system satisfies the safety specification relative to the world model. And in the most paradigmatic case, we could imagine that this looks like a formal proof. So if we get AI systems that can reason mathematically much faster than humans and at a larger scale than humans, then this could be used to much more tractably produce such proofs. And this, of course, is a field that has existed since the very start of AI, and there are lots of efforts for incorporating large language models and so on into these efforts. If we can get a situation where capabilities in automated theorem proving sort of automatically scales with capabilities of AI systems more generally, then the hope is this could make such formal verification feasible. And here again, we have a spectrum of approaches where some sort of rigorous statistical testing could give you weak guarantees with certain assumptions. I mean, these are the kinds of things that people develop in statistics, right? If you run such and such test and with such and such probability, you can ensure that some probability is less than something, etc., etc. And then this goes up all the way to the level where you have a complete proof that the safety specification is met. And it's also important to note here that the proof wouldn't necessarily have to be, oh, the safety specification is met with probability 1. It could be the probability of failing to meet the safety spec is at most epsilon, given some further assumptions.
Your examples of self-driving cars and drug development and stuff, I mean, I find those hard to map to, absolute logical criteria that would be guaranteed. It's, we want to see cars that have accidents less often than human drivers do, but nobody ever thinks you're ever going to meet perfection. And a drug always has a potential to kill somebody. We hope it's doing more harm than good. So, I mean, do trade-offs fit into a logical framework like this? Fine. It sounds like you kind of said at the end they do. But it seems, doesn't that kind of reduce to a statistical guarantee again, like under a given distribution? If we sample from a distribution in terms of real behavior on autonomous cars, we can't trust that behavior will be representative of what happens, down the road as distribution shift. So anyway, yeah.
Yes. So certainly, depending on what counts as a failure and how you're using your system, some failure rate will have to be tolerable. Now, of course, if you're driving a car, probably that a much higher failure rate is acceptable as opposed to if you're controlling an arsenal of nuclear weapons, for example. But yes, you can never get the error rate down to 0, if not else, because the world model isn't guaranteed to be correct, right? Just because you've proven, even if something holds with probability 1 relative to a particular model, that does not in the real world mean that it's impossible, right? This is, there are many cases where someone produces some proof that a certain cryptographic protocol can't be broken, and then someone finds a way to break it in practice because some assumption behind that proof turns out not to hold in some scenario. So this is absolutely true, and but you can also bake this into both your safety specification. You could specify a maximum rate of error, or in the proof method. So, maybe you have some probabilistic bound that your proof method, the probability that it will miss a counterexample is at most something. But I don't think that this means that you're essentially back to the same situation as you are with just empirical testing. And I think we can see this if we just look at some real-world examples. So let's say that you're building a nuclear power plant. Now, if you do this, you will have various forms of rigorous analysis of the components of your nuclear power plant to ensure that the probability of a meltdown is very low. Now, of course, meltdown can still happen, but here the uncertainty looks less like, oh, well, we just ran this power plant for a while and it didn't blow up, so probably it won't. That type of guarantee is weaker still than the guarantee that you get if you say, within this model, if all the assumptions are met, then for this duration of operation, the probability of a meltdown is low. And an important reason that they're different is also that you have a very clear sense of what the exact assumptions are. Neural networks, right? There are many cases where you train a neural network we have the classic example, to recognize cats and dogs, and you get 99% accuracy in your test set. But then it turns out that all the pictures of dogs were taken outdoors and all the pictures of cats were taken indoors. So the neural network is actually just looking for green pixels. Turns out this correlates well with cats and dogs. And if you had a sort of a more mechanistic understanding of the network, you would be able to say, well, this network is 99% accurate, but only under these very specific assumptions, whereas some other network might have the same test score on the same data set, but be valid in a much wider range of circumstances.
I get the notion of trying to get away from use case-based testing for something that is a trained artificial intelligence operating in the world, but I'm still unclear as to what the content of the model, this thing you call a model. Every time you say the word model, to me, when I model, and I've done a lot of data modeling of domains. Domains are pieces of a world, right? And when I model that, what I model is how that works, how that model, how that universe, how that domain operates. Who are the actors? How do they interact? How do they relate? But every time you talk about it, it sounds like you're saying what you're looking for is a set of rules about outcomes. And that's a very different kind of model. And so I'm a little confused about that. I'm confused as to whether you're trying to say, I don't want to use your nuclear power plant example. My model says the nuclear power plant can't melt down. Well, that's a rule about an outcome. It's not a description of how the nuclear power plant operates and what universe it operates in. And so I'm a little confused about that, and I'd appreciate some clarification.
So rules about outcome is what you want to get to at the end. But in order to get there, I believe you need to model the dynamics of the domain. So in the nuclear power plant example, you would need to model things about particle physics. You would need to model various facts about the engineering of the machines in the building. You might have to model facts about the accuracy of the workers in that power plant, how often they make a mistake. You might have to model, I don't know, things about the weather, things about energy requirements. I don't know. I don't design nuclear power plants, but you need all of those dynamics of the domain in order to then determine, and if I put this controller in this context as described by the model, then the dynamics of the model would predicts that some outcome wouldn't happen, say. More abstractly, I suppose, you could say that a world model consists of a bunch of variables, including potentially unobservable variables, with the requirement that these variables are stated at a level of abstraction where you can specify your safety specifications in terms of those variables, and you can also model the dynamics of those variables over time, subject to certain interventions or actions by the AI system. Does that explain it?
Yeah, although the complexity of, modeling the domain of a nuclear power plant
Yes.
is, I mean, to some extent, a lot of folks are using machine learning as a replacement for modeling that complexity because it's really hard, right?
Yes.
To capture all of the dynamics and relationships in a real world environment.
Yes.
So I'm wondering, so the thing that occurs to me, the thing I'm wondering about is are you not creating a problem that's just as big as the original problem? And that's what I'm sort of chewing on right here.
I agree. That's a very important point, that creating the world model is incredibly hard. And if you just use machine learning to create that model, or if you have a model that you can't test in any meaningful sense, then yes, you're basically back in the same situation as you started in. But I think there is hope, for example, that depending on the context of use for an AI system, you might have a case where the model doesn't have to be maybe as complicated, or a situation where it can be interpretable. So if we think of in a medical situation, maybe you could have a model of cell biology that is in fact at a level of complexity where you can either check it manually or test individual pieces of it in isolation from the rest of the model. And if you use a strategy such as use LLMs to write probabilistic programs, then you'd have a setup where you can create a very large model scalably using computers, but where the resulting model is still interpretable, which means that you can look at it, you can inspect it and see if there seems to be anything stupid in there, or you can test parts of that model in isolation. Whereas if you train a giant black box model on just input to outcome relations, then you can't inspect its internals and you can't test individual assumptions separately from the rest. So yes, that is to say that is a huge difficulty, but I think not necessarily in such a way that you simply end up with the same problem you started with.
When you think about these AI systems, they're so complex. I mean, we can completely understand what each neuron does, but we can't understand what the 1.5 trillion neurons in GPT does. So, to model what its possible responses might be is not in a way that we can logically reason about. Just doesn't seem possible, I guess, unless there's something I'm not seeing. I mean, I do see some things are modelable, and I do see some techniques, like maybe finding adversarial examples, might be part of a proof system. But I don't know. How does that figure in?
Well, so we can't get the sort of overview of how something like ChatGPT works, but we can absolutely model it. I mean, it is itself a computer program, right? So we have a perfect model of exactly what it would do in any situation. The difficulty, of course, is that the scale of the program is such that a human can't reason about that in any on any useful time scale. But if you have another AI system that does a proof search in some way, then it might be able to do this at a speed and scale that is sufficient for a system of that size. And of course, if you produce, let's say for the sake of example, something like a proof in Lean, then you can verify that the proof is accurate, even if this proof has trillions of lines and is too big for a human to understand. Basically, the hope is that machines will do the thinking and then produce proof certificates that we can verify without having to trust the AI systems that produce the proofs. So get proofs that can be verified independently.
I'll try phrasing my question in three parts. And I a little bit about my background. I've actually done some amount of world modeling in a multi-agentic system, just trying to figure out, and again, researching, building consistent models of the world. I feel like point one, the ability to build a world model itself, I think, is questionable, number one. Quite simply, this is the same argument against multi-agent modeling, which is that there are far too many parameters in the world to model. And we don't even know, like you mentioned, there are some parameters that we don't even know what they are. That's, I think, critique number one. Critique number two is that in general multi-agent paradigms, you have emergent scenarios, right? You have actors acting, and you might be spending, and you might be thinking about different failure cases and success cases, which may never happen in reality. They might just be emergent phenomena inside of the model that you've built. And number three, at the end of the day, it's still a model. At best, what you've done is you've simulated the real world. It's not the real world. And there are basic proofs in science, like the observer effect, where just observing a system means that you're potentially affecting the system. How do you counter against things like that?
Yes, there are many things in there. So the first thing is that, yes, of course, some parts of the real world are intractably difficult to model, and especially agents and the things that happen when agents reason about each other and so on would be incredibly complex. I mean, if you wanted to create an interpretable model of humans, then that would necessitate creating an interpretable general AI system, because such a model would be a general AI system. So there probably are things that you can't reasonably model in an interpretable way. And then we have things like chaotic dynamics, right? We know that some things, unless you can measure the world with infinite precision, even if it's deterministic, you can't predict beyond certain horizons and so on. And you need to be aware of this, right? However, this does not necessarily mean that you can't model these systems. It just means that you need to have a wider margin of error, basically, in your model. So you can say, well, here I have some chaotic system, and I know after a certain time period, the parameters of this system will lie within some range, but you can't determine the exact point in that range. And yeah, that can happen, and your model should take those kinds of issues into account. But this doesn't mean that you can't create models that are adequate to ensure certain safety properties. So, for example, you might use your AI system in a situation that is just simpler, where these kinds of things don't happen for some reason. Another reason is that perhaps even with these higher error bars or more non-determinism in the model, that might still be adequate to prove the safety property. So you have some like, well, I can't determine if the real world parameters are this, or this, but for all parameters in this set or that conform to some assumption, you can still ensure that some safety property holds. Another thing to note is that you can, for example, run your world model in parallel with your AI system. And then if the world model ever makes an observation that the world model predicts is impossible, then you can transition your AI system to some safe mode, and thereby ensure that, or at least make it much less likely, that you will encounter a a scenario that's outside the range of your world model. Yes, all of this is to say that, yes, creating a completely general model of everything in the world, that's not feasible. But this doesn't mean that you can't create a model that's good enough for the safety properties that you are interested in. I mean, again, this is something that's done all the time in specific cases. Yes, as a computer scientist, sure, you have at some point proven that a particular computer program will always terminate in some number of steps for any input. And yeah, for that type of case, chaotic dynamics, and that doesn't matter.
If at some point AI systems start improving themselves, and I assume it's possible, right? I don't know what this probability, but it's definitely possible that AI will be improving itself. And most likely it will be improving itself very, very fast, that humans won't be able to react on this. So we might end up in a situation that the world has changed already because AI has done something, has changed, but we didn't have even an opportunity to react and take actions. So my question is, when you guys were developing this framework, did you sort of anticipate this kind of scenario that, you know, the disaster has happened and we even didn't have opportunity, like, you know, to react on it or even understand that it has happened?
These kinds of scenarios is something that I at least certainly had in mind while working on this. And I think that when it comes to AI systems improving themselves, that will definitely happen. The open question to me at least is what sort of upper limit they approach and how quick that process is. But I think that in order to ensure that humanity stays in the driving seat, we need to ensure that AI systems are safe before they are able or allowed to do something like that. The research agenda that's laid out here is definitely something that requires more time to implement. So if AI development goes very quickly, it might not be possible to implement these things. And so depending on how things go, it might be that this would only help if combined with intentional efforts to slow down certain types of AI development. So if we notice that AI systems are able to improve themselves very quickly, it might be a good idea to say, to have some sort of agreement that, you know, let's maybe not go down that rabbit hole before we really know what we're doing. And I think that's, we're not at a point where we know what we're doing right now. So yeah, I agree. That's a very important thing to keep in mind. And it's, at least in my opinion, not something that this solves per se, at least not without further additions of various types.